So in this segment, we're going to talk about the lifetime of stars. How long do they last on the main sequence, fusing hydrogen to helium and maintaining hydrostatic equilibrium? Well, it turns out that it all depends on the mass of the star. From the protostar phase right down to the lifetime of the star, and then in later lessons we'll see how the stars die, is all a matter of mass. For stars, size definitely counts. Because the greater the mass, remember all of this is happening, everything that happens to the star is a result of gravity pulling the matter of the star together. And the more mass you have, the stronger the gravitational force will be. And the stronger the gravitational force, the more gravity is going to squeeze that hydrogen together, and the higher the temperature will be. And the higher the temperature, the faster hydrogen nuclei will be smashed together in the core, the higher the fusion rate will be, and the faster the star will burn through all of its nuclear fuel, and the shorter will be its lifetime. Now that applies even for the protostar phase. Just to give you some examples, we think our own sun probably took about 30 million years to collapse, to begin its collapse, turn into a protostar, and then get hot enough at its core, that 10 million Kelvin, to ignite its nuclear engines. A star, on the other hand, that has half the mass of the sun is going to have a harder time contracting because there's less gravity, and it might take 100 million years rather than 30 million years to collapse and reach that point of nuclear ignition. Twice the mass of the sun might only take 8 million years. A star that's pretty big, 15 solar masses, might collapse in only about 160,000 years. Now, let's just take a short little detour to mention, what about stars that don't actually have enough mass at all to start nuclear fusion in their cores? That cutoff, that limit, seems to be at about 8% of the mass of the sun. That's the 0.08 solar masses. Any clump of hydrogen that's contracting that has 8% of the solar mass or less simply will never be able to heat up to 10 million Kelvin in its core. There's just not enough gravity pulling everything together. So what will happen to that clump of gas? It's going to keep contracting and glowing basically like a protostar, but it will glow for billions and billions of years, gently running out of this energy that's coming from the gravitational contraction. We call such an object a brown dwarf. A brown dwarf can be thought of as kind of halfway between a gas giant planet. It's bigger than Jupiter, but it's smaller than a star. So it's kind of it's a failed star, so to speak. But they're interesting in their own right, and in recent years, much study has been done on brown dwarfs. This is kind of a whole new area of astronomical studies.
Stars are temperamental creatures, their frames of mind determined by the physics of fusion. Our own sun is presently a little agitated, as it gets every 11 years or so. But now astronomers operating the European Southern Observatory's Very Large Telescope are checking on the mood of the closest brown dwarf star to the sun, orbiting the center of our galaxy about 6 light years out from us, in the constellation called Vela, the Sail. Known to its friends as Lumen 16b, it's one of a binary pair of old, cool brown dwarf stars, so dim they were discovered only recently, in 2013, by astronomer Kevin Lumen as he sifted data taken by the WISE infrared survey mission. Such stars lack enough mass to start fusing hydrogen in their cores. They will never glow very brightly. But as dim as Lumen 16b is, the ESO team was still able to map brightness variations in its mottled atmosphere as the star rotated. Feeling the vibes on other stars is more than just a scientific party trick. By comparing the dispositions of various star types, scientists are gaining valuable clues to predicting solar weather affecting Earth and our human-made satellites, and to anticipating our Sun's long-term variations, which affect Earth's climate. For Space.com, I'm Dave Brody.
So the same principle applies when we look at the main sequence lifetime of a star, the time it spends fusing hydrogen in its core. The more massive the star, the faster it will burn through its fuel because it has more gravity, and the shorter will be its time on the main sequence. Big stars live fast and die young. To give you some examples, here again is the sun with its one solar mass, and we calculate that the lifetime of the sun will be about 10 billion years. It's been fusing hydrogen at 600 million tons every second for about 5 billion years, and it's about halfway through its life. It's going to do that for another 10 billion. A tiny little star that's only 1/10 the mass of the sun will never get as hot. It's an M7 class here, but it's going to live for trillions of years. Thousands of billions is trillions. On the other hand, an F-class star is hotter because it's more massive, so 1.5 times, say, the mass of the sun. That's approximately like Sirius, the brightest looking star in the night sky. It's only going to live for 3 billion years. That's only 30% of the sun's lifetime. And as you get more and more massive, the lifetimes get shorter and shorter and shorter. So an O-class star, even a relatively cool O-class star, only lasts for 10, 20 million years as opposed to 10 billion. That's 1,000 times faster that it burns through all of its hydrogen. You can see that on this graph here, that the time here and the solar masses. So here is the sun with its solar mass of 1, living about 10 billion years. If you have a star of about 5 solar masses, it's only going to live maybe 110 million years. On the other hand, if it's only half a solar mass, then it's going to live for about 100 billion years instead of only 10 billion years, 10 times the life of the sun. In the next lesson, we'll do a very little bit of math to actually calculate numbers for main sequence lifetimes from the mass of the star.